March 2024. A machine shop in Akron, Ohio. The rhythmic hum of a 110-year-old engine lathe fills the workspace as its massive cast-iron bed supports a 4-ton steel forging spinning at precisely 180 RPM. The lathe's operator, a third-generation machinist named Robert Chen, guides a carbide cutting tool across the workpiece, with movements measured in thousandths of an inch. The machine hasn't failed in 3 generations of his family's ownership. Modern CNC lathes surrounding Chen's vintage equipment cost $300,000 each and carry warranties promising 15 years of service before major rebuilds become necessary. The 1914 lathe beside them cost $1,200 when new, equivalent to $37,000 today, and has operated continuously for 110 years without requiring a single major component replacement beyond routine bearing changes and drive belt updates. No planned obsolescence, no computer controls requiring proprietary software updates, no expectation that the machine would become a disposable asset after a predetermined service life. This lathe was engineered under manufacturing principles that treated heavy equipment as century-long investments, not depreciating capital expenses. The engineering specifications revealed design philosophy fundamentally different from modern manufacturing equipment. The main bed weighs 400 pounds of continuous cast iron poured in a single piece, creating structural rigidity that absorbs vibration and maintains geometric accuracy under cutting forces that would deflect lighter machines. The headstock assembly uses bronze bearings 6 inches in diameter, hand-scraped to tolerances of 0.01 inches, supporting a spindle shaft machined from solid steel. Every component was over-engineered by modern standards. Gears cut from solid forgings rather than stamped from sheet metal. Drivetrains designed for loads 3 times greater than the machine's rated capacity. Lubrication systems that delivered oil to every bearing surface through gravity-fed reservoirs requiring no pumps or electrical components. But in 1914, these specifications weren't celebrated as superior engineering. They were criticized as wasteful, impractical, and commercially suicidal by machine tool manufacturers who had built successful businesses selling lighter, faster, cheaper equipment to factories demanding maximum production speed and minimum capital investment. The question isn't why the 1914 lathe lasted a century. The question is why an entire industry rejected the engineering principles that made such longevity possible, and why factories initially refused to buy machines designed to outlast their grandchildren. Chicago, Illinois. September 1908. The National Machine Tool Builders Association convention filled the Palmer House Hotel's grand ballroom with manufacturers showcasing their latest innovations in metalworking equipment. William Sellers, Jr., sales director for Cincinnati Machine Tool Company, gestured toward his company's new Model 16 lathe, which weighed just 3,200 pounds, less than half the weight of comparable equipment from just 5 years earlier. Speed and efficiency, Sellers announced to the crowd of factory purchasing agents examining his display. Our new lightweight design reduces floor loading, simplifies installation, and cuts shipping costs by 6%. Most importantly, it accelerates from 0 to full speed in 8 seconds, compared to the 45 seconds required by those outdated heavy machines. The audience nodded approvingly. Henry Ford's moving assembly line had revolutionized manufacturing philosophy, creating demand for machine tools that prioritized rapid production cycles over long-term durability. Factory owners calculated profitability in terms of parts produced per hour, not decades of service life. Equipment that accelerated quickly between operations, even if less stable during cutting, generated higher throughput and better return on investment. Lightweight construction aligned perfectly with early 20th century economic pressures. Labor costs were rising as skilled machinists demanded higher wages for operating increasingly complex equipment. Material costs for cast iron and steel had increased 40% since 1900, making lighter machines significantly cheaper to manufacture. Transportation expenses favored equipment that could ship via standard freight cars without requiring specialized heavy load handling. The technical arguments supporting lightweight design seemed economically rational. Most machine shops produced relatively small parts for agricultural equipment, household appliances, and light industrial machinery. These applications required lathes capable of handling workpieces under 100 pounds and removing material in shallow cuts that generated minimal cutting forces. Heavy cast iron beds and massive bearing assemblies appeared wasteful when machining brass fittings or turning steel shafts just 2 inches in diameter. Manufacturing trade journals reinforced this perspective through articles celebrating the modern, efficient machine shop, equipped with lightweight, high-speed equipment that maximized production velocity. Machinery Magazine's 1909 feature on progressive factory management praised Cincinnati Machine Tools' new facility where not a single machine weighs over 4,000 pounds, yet daily production exceeds facilities using equipment twice that weight. Financial incentives accelerated the trend toward lighter construction. Banks offering equipment loans preferred faster asset turnover, encouraging factory owners to purchase cheaper machines with shorter expected lifespans. Accounting practices treated machine tools as depreciating assets, making the initial purchase price more important than long-term maintenance costs or replacement frequency. But the lightweight revolution created vulnerabilities that wouldn't become apparent until industrial demands exceeded the equipment's fundamental capabilities. Cincinnati, Ohio, January 1914. James. Lodge stood in his company's pattern shop examining the wooden forms that would create molds for the heaviest lathe his company had ever designed. At 68 years old, Lodge had spent 40 years building machine tools, and he was about to risk his company's reputation on engineering principles that contradicted every trend in modern manufacturing. The specifications seemed almost perverse by contemporary standards. A main bed casting weighing 8,400 pounds. Nearly 3 times heavier than competing lathes of similar swing capacity. A headstock using bearing surfaces 6 inches in diameter when competitors were reducing bearing sizes to minimize friction and improve acceleration. A gear train designed for 40 horsepower loads when the lathe's motor produced just 7.5 horsepower. Lodge's partner, Nathaniel Shipley, had questioned the design during the previous year's planning sessions. We're building a lathe that costs 40% more than competing equipment, weighs enough to require reinforced flooring, and accelerates slower than any machine our customers currently operate. Cincinnati Machine is selling lightweight lathes at $8. We're proposing to charge $1,200 for equipment that appears less capable by every measurement factory owners actually care about. But Lodge had witnessed firsthand the limitations of lightweight construction. His company's service department received constant complaints about machines losing accuracy after just 3 years of operation. Lightweight beds flexed under cutting forces, causing dimensional errors that machinists corrected through skill rather than mechanical precision. Thin wall castings cracked from thermal cycling as machines heated during operation and cooled overnight. Small bearings wore rapidly under the shock loads generated by interrupted cuts, requiring frequent adjustment and eventual replacement. The engineering philosophy behind Lodge and Shipley's 1914 lathe rejected the assumption that machine tools were disposable assets. Lodge believed that properly designed equipment should maintain accuracy for decades, not years. That belief required design decisions directly opposite to industry trends. Massive castings that absorbed vibration instead of resonating with cutting forces, oversized bearings that would survive a century of operation, and structural rigidity that prioritized geometric stability over weight reduction. The lathe's design incorporated innovations that addressed specific technical challenges Lodge had identified in lightweight machines. The bed casting included massive internal ribbing that created a box section structure significantly stiffer than competitors' simple rectangular forms. The headstock bearings received oil through gravity-fed reservoirs that required no pumps, no seals, and no maintenance beyond periodic fluid-level checks. The gear train used gears cut from solid steel forgings, each gear requiring 40 hours of machining time rather than stamped components that wore quickly under load. Lodge and Shipley's sales director, Thomas Webster, understood the commercial challenge the new lathe represented. We're asking factory owners to pay premium prices for benefits they won't appreciate until their competitors' machines have failed. That's not a compelling sales proposition in 1914. But Lodge had committed $45,000, nearly half his company's annual profits, to developing patterns, tooling, and manufacturing capabilities for the heavy lathe. The first prototype would complete machining in March 1914, followed by a demonstration period that would determine whether American industry valued long-term precision over short-term economy. Detroit, Michigan, April 1914. John Patterson, purchasing agent for Detroit Manufacturing Company, stood beside Lodge and Shipley's new heavy-duty lathe in his factory's machine shop, shaking his head with visible frustration. Thomas Webster, who had traveled from Cincinnati to oversee the demonstration installation, recognized the expression of a buyer who had already decided against purchasing. 48 seconds from stop to full cutting speed, Patterson said, consulting his stopwatch. Our Cincinnati lathes reach full speed in 9 seconds. Your machine produces 6 parts per hour. Theirs produce 11. The mathematics are simple, Mr. Webster. Your lathe costs more, produces less, and requires reinforced flooring that adds another $3 to installation costs. Webster had encountered variations of this objection at every demonstration over the previous 3 months. Factory owners evaluated machine tools using metrics that favored lightweight construction, parts produced per hour, floor space utilization, installation costs, and initial purchase price. The heavy lathe's advantages, long-term accuracy, vibration damping, and century-scale durability, appeared on no purchasing department spreadsheet in American manufacturing. The commercial reality was devastating. Lodge and Shipley had manufactured 12 heavy lathes during the spring of 1914. They had sold 3, 2 to railroad maintenance shops that needed equipment capable of machining locomotive axles, and 1 to a specialty machine shop whose owner was James Lodge's personal friend. 9 lathes sat in the company's warehouse, representing $10,800 in unsold inventory that threatened to bankrupt a company with just $78,000 in annual revenue. Machinists who actually operated the heavy lathes reported their own frustrations. The massive equipment required different techniques than lightweight machines. Starting a heavy workpiece spinning demanded patience as the lathe's momentum gradually built to operating speed. Making setup adjustments took longer because the machine's weight resisted the quick positioning changes that characterized efficient production machining. Even simple operations felt cumbersome compared to lightweight lathes that responded instantly to operator inputs. The skilled workers who had mastered lightweight equipment saw no reason to relearn machining techniques for equipment that appeared to offer no practical advantages. The heavy lathe's stability during cutting operations was invisible. It simply didn't vibrate, which seemed unremarkable to machinists who had learned to compensate for vibration through technique. The precision that would remain unchanged after 30 years of operation meant nothing in 1914 when the machines were brand new. Trade publication reviews reinforced negative perceptions. American Machinist magazine's June 1914 evaluation concluded that, while Lodge and Shipley's heavy-duty lathe demonstrates impressive build quality, its practical applications appear limited to specialized heavy work that represents a small fraction of American manufacturing demand. The company's decision to prioritize weight and rigidity over speed and economy seems commercially questionable. By August 1914, Lodge and Shipley had stopped manufacturing the heavy lathe entirely, with 17 unsold units consuming warehouse space while the company's salesmen focused on selling lighter equipment that actually generated revenue. James Lodge, who had invested his reputation and his company's capital in engineering principles he believed represented superior manufacturing philosophy, appeared to have misread American industry's actual requirements. The heavy lathe seemed destined to become a footnote in machine tool history, an example of excellent engineering that failed commercially because it solved problems that customers didn't know they had. Then European events transformed American industrial requirements overnight. Bethlehem, Pennsylvania, November 1914. Charles Schwab, president of Bethlehem Steel Corporation, stood in his company's machine shop examining a pile of rejected artillery shell casings that represented $18,000 in wasted material and labor. Each casing showed the same defect, dimensional variations exceeding acceptable tolerances by 0.008 inches, making the shells unusable for British military contracts that demanded precision matching with artillery breeches manufactured in England. Eugene Grace, Bethlehem Steel's production superintendent, explained the technical challenge. Our Cincinnati lathes can't maintain accuracy when machining these heavy steel forgings. The cutting forces deflect the machine beds, creating tapers we can't correct. We're rejecting 30% of casings after final inspection. World War I had created unprecedented demand for heavy military components that exceeded lightweight lathes' capabilities. Artillery shells weighing 180 pounds each, tank armor plates requiring precision boring operations on steel 4 inches thick, ship propeller shafts 18 inches in diameter, naval gun components tolerating no dimensional error greater than 0.002 inches across 6-foot lengths. Lightweight machines attempting to machine these components flexed under cutting forces like tree branches bending in wind. The beds twisted, slightly but measurably, causing cutting tools to deviate from intended paths and producing parts that looked dimensionally correct but measured out of tolerance under precise inspection. Machinists compensated by reducing cutting depths, which increased production time by factors of 3 or 4 while still not guaranteeing acceptable accuracy. Grace had heard about Lodge and Shipley's heavy lathe from a machinist who had operated one at a railroad shop. Bethlehem Steel ordered 2 units for evaluation in December 1914, paying premium prices that Lodge and Shipley had abandoned hope of receiving. The machines arrived in January 1915 and began machining artillery shell casings immediately. The difference was visible even to untrained observers. Lightweight lathes chattered and vibrated during heavy cuts, producing parts with rough surface finishes that required secondary grinding operations. The heavy lathe cut silently, its massive bed absorbing forces that deflected lighter machines, while its oversized bearings maintained geometric accuracy under loads that would quickly wear standard bearing assemblies. Production data told the story quantitatively. Lightweight lathes averaged 6.2 acceptable artillery casings per 8-hour shift, with rejection rates of 28%. The heavy Lodge and Shipley lathe produced 4.8 casings per shift, fewer parts overall, but rejection rates dropped to 3%. When accounting for material costs and rework time, the heavy lathe's cost per acceptable part was 4% lower despite slower production speed. More significantly, the heavy lathe maintained accuracy while removing metal in single passes that required 3 cuts on lightweight equipment. A 0.500-inch depth of cut that would stall or damage lighter machines represented routine operation for equipment designed with massive structural margin. This capability transformed production economics for heavy parts where cutting time dominated cycle time. By March 1915, Bethlehem Steel had ordered 12 additional Lodge and Shipley heavy lathes. By June, they had ordered 48 more. Eugene Grace's purchasing requisitions noted that these machines represent the only equipment capable of maintaining military specification tolerances while machining heavy steel components under production conditions. Other military contractors faced identical challenges. Remington Arms needed lathes for machining rifle barrels. Winchester required equipment for producing artillery shell fuses. Electric Boat Company demanded precision machines for submarine components. Every contractor discovered that lightweight equipment that had seemed adequate for peacetime manufacturing couldn't handle wartime production requirements. Lodge and Shipley's warehouse inventory of unsold heavy lathes disappeared within 3 months. The company's manufacturing capacity couldn't meet demand from military contractors who suddenly understood that weight wasn't a disadvantage. It was the fundamental requirement for machining heavy components with precision. Flint, Michigan, May 1923. Walter Chrysler stood in his new automobile manufacturing facility examining the machine shop that would produce engines for his company's first vehicles. His purchasing agent recommended Cincinnati Machine Tools' latest lightweight lathes, which dominated automotive manufacturing. Chrysler overruled the recommendation and ordered Lodge and Shipley heavy-duty equipment that cost 60% more and required reinforced flooring. "I watched lightweight machines fail at Buick," Chrysler explained to his confused purchasing staff. "They produce parts quickly when new, but lose accuracy after 3 years. Then we spend fortunes on inspection, rework, and warranty claims. The Lodge and Shipley lathes cost more initially, but will still be producing precision parts when we're building our 100,000th automobile." The post-war decade vindicated the heavy lathe's engineering philosophy across American manufacturing. Companies that had purchased lightweight equipment during the war discovered that rapid production had degraded their machines to the point where accuracy was no longer achievable. Beds had worn from inadequate bearing support. Castings had cracked from thermal cycling. Gear trains had worn from shock loads they were never designed to handle. Repair costs for lightweight machines frequently exceeded replacement prices, but replacement simply restarted the degradation cycle. Factory owners who performed honest cost accounting discovered they were replacing lightweight lathes every 8 years on average, effectively paying the equipment's purchase price repeatedly while suffering through progressive accuracy loss between replacement cycles. Heavy Lodge and Shipley lathes operating in the same factories showed no measurable accuracy degradation after a decade of service. The massive castings that critics had mocked as wasteful proved essential for maintaining geometric stability as machines absorbed years of thermal cycling and cutting forces. The oversized bearings, dismissed as over-engineering, showed no measurable wear after machining millions of parts. The competitive advantages became undeniable in precision manufacturing sectors. Aircraft engine manufacturers discovered that lightweight lathes couldn't maintain the 0.001-inch tolerances required for crankshaft journals. Machine tool builders found that their own products required precision machining that only heavy lathes could reliably provide. Even manufacturers producing relatively simple parts recognized that consistent accuracy reduced inspection costs and virtually eliminated rework expenses. By 1925, Lodge and Shipley couldn't manufacture heavy lathes fast enough to meet demand. Their competitors, including Cincinnati Machine Tool, which had pioneered lightweight construction, began designing heavy-duty equipment that copied Lodge and Shipley's structural principles. Cast iron beds increased in weight from 3,000 pounds to 7,000 pounds. Bearing diameters grew from 3 inches to 5 inches. Gear trains shifted from stamped components to machined forgings. The transformation occurred across every machine tool category. Milling machines, drill presses, grinders, and shapers all increased in weight as manufacturers recognized that structural rigidity determined long-term precision. Industry trade publications that had celebrated lightweight design in 1910 now featured articles explaining why modern manufacturing demands equipment built for permanence rather than economy. Technical specifications that seemed extravagant in 1914 became minimum standards by 1930. Machine tool buyers demanded continuous cast iron beds, oversized bearing assemblies, and structural components designed for loads exceeding normal operating requirements by factors of 3 or more. The purchasing criteria that had nearly bankrupted Lodge and Shipley 15 years earlier now defined industry expectations. The heavy lathes' influence extended beyond machine tool design into manufacturing philosophy itself. Companies began treating production equipment as long-term capital investments, requiring the same careful specification and maintenance as factory buildings. Accounting practices shifted from aggressive depreciation schedules to amortization periods, recognizing that properly engineered equipment could serve for decades without substantial degradation. The engineering principles that James Lodge had championed against market resistance became the foundation for American manufacturing dominance throughout the mid-20th century. Cleveland, Ohio. Present day. Michael Torres, a manufacturing engineer for an aerospace components company, watches a 1914 Lodge and Shipley lathe machine, a titanium turbine housing with geometric tolerances of 0.0005 inches, precision that some modern CNC equipment struggles to maintain consistently. The lathe has operated in various Cleveland machine shops for 110 years, changing owners 6 times but never requiring major structural repairs. Modern machine tool manufacturers specify replacement intervals of 15 years for production equipment, after which maintenance costs supposedly exceed replacement prices. The mathematics suggests that Torres's company should have replaced that 1914 lathe 7 times by now, spending over $2 million on successive generations of equipment. Instead, the single machine purchased for $12,200 in 1914 continues producing parts that meet aerospace specifications written a century after its manufacture. The engineering contrast reveals a philosophical divide that transcends simple technical differences. The 1914 lathe was designed under the assumption that machines should outlast the people who built them, maintained by the same craftsmanship principles that created medieval cathedrals or Roman aqueducts. Modern equipment embodies opposite assumptions: that technological advancement makes longevity irrelevant, that replacement is economically superior to repair, and that manufacturing equipment represents consumable assets rather than permanent infrastructure. Contemporary machine tool catalogs specify controller software that becomes unsupported after 10 years. Proprietary components available only through manufacturer-authorized distributors, and electronic systems virtually impossible to repair when components fail. The 1914 lathe uses no computers, no proprietary parts, and no components that require specialized knowledge to repair or replace. Every bearing, every gear, every adjustment mechanism can be maintained by competent machinists using standard tools. The weight that critics denounced as wasteful in 1914 explains why these machines maintain precision after a century of operation. 8,000 pounds of continuous cast iron doesn't wear, doesn't deflect, doesn't degrade from thermal cycling. The massive structure that seemed excessive when new becomes essential as decades pass and lighter machines fail from the accumulated stress of production service. Industrial historians recognize the 1910 lathe as representing peak mechanical engineering, the moment when designers understood materials deeply enough to create machines that would function indefinitely under normal operating conditions. Later equipment incorporated more sophisticated controls and automation, but never again matched the fundamental structural integrity that made century-scale longevity possible. The broader lesson transcends machine tools entirely. The same engineering philosophy that created 110-year-old lathes, built Hoover Dam, Brooklyn Bridge, and transcontinental railroad infrastructure that continues functioning generations after construction. These projects assumed that great engineering should outlast its creators, serving purposes that extend beyond immediate economic return into legacy and permanence. Modern manufacturing has abandoned this philosophy almost entirely, creating equipment designed for obsolescence and replacement rather than longevity and repair. The economic arguments supporting this approach seem rational until examining actual costs. Companies replacing $300,000 CNC lathes every 15 years spend more over a century than factories that purchased a single 1914 machine that's still running today. The 1914 lathe, they said, was 2 heavy stands in Cleveland's machine shop as testament to engineering principles that modern manufacturing has forgotten. It proves that planned obsolescence wasn't always inevitable, that machines could be built to serve generations, and that the weight critics once mocked was actually the foundation for precision that would span a century. The question isn't why the 1914 lathe lasted so long. The question is why we stopped believing that machines should.